Okay, good morning. Welcome back to the classroom. Today, let's have a look at the fifth lesson of chapter 5, dot product of vectors in two space. First, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concept of dot product for both geometric vectors and Cartesian vectors in two space. Determine the dot product for both geometric vectors and Cartesian vectors in two space. Understand the properties of dot product in two space. Find the projection of one vector on another in two space, and then solve application problems related to the dot product in two space. Okay, first of all, let's have a look at the concept of the dot product for geometric vectors. For two vectors A and B, the dot product is defined as dot product of A and B equals the magnitude of A times magnitude of B times cosine theta, where theta is the angle between vector A and B when the vectors are arranged tail to tail. And theta is between 0 and 180 degrees inclusive, both ends. The dot product is a scalar, not a vector. According to this formula, we can easily see that, right? And the units depend on the application. If either A or B is a zero vector, then the dot product of A and B equals zero vector. Oh, sorry, not a vector, equals 0. Note the dot product is always a scalar, not a vector, right? Okay, I'll give you some time to have a look at the concept here. Any questions, just let me know, okay? Okay, any questions? No questions? Then let's have a look at an example. Can you determine the dot product of each pair of vectors below? Okay, I'll give you 3 minutes. You have a look at this question by yourself. Okay, have you finished? Okay, let's have a look at the solution together. So according to the definition of dot product of two vectors, in question A dot product with B equals the magnitude of A times magnitude of B times cosine theta. Theta is the angle between A and B. So substitute all the values in. That gives us the the dot product of A and B is approximately 459.6. So in question B, dot product of M and N equals 60 times 75 times cosine 90 degrees, which is 0. In question C, dot product of U and V equals 100 times 85 times cosine 120 degrees, which gives us negative 4250. Okay, any questions? Okay, if no questions, let's have a look at the dot product for Cartesian vectors. Dot product can also be defined for Cartesian vectors. So if we let vector A equals A1, A2, that's position vector for vector A, and vector B is B1, B2, also the position vector for vector B. Then from the geometric definition of the dot product, we have dot product of A and B equals magnitude of A times magnitude of B times cosine theta. Theta is angle between A and B, right? From the triangle on the right, we know vector C equals A minus B, which is A1 minus B1, A2 minus B2, right? Therefore, by the cosine law, we know the magnitude of A squared equals magnitude of A squared plus magnitude of B squared, minus 2 times the magnitude of A times magnitude of B times cosine theta. Then that gives us magnitude of A times magnitude of B times cosine theta equals magnitude of A squared plus magnitude of B squared minus magnitude of C squared over 2. And also, we can find the magnitude of A, B, and C using their position vectors, right? So put all the values in and simplify the expression. That gives us the dot product of A and B actually equals A1, B1 plus A2, B2. Therefore, we have the following conclusion. If we have two vectors, A, which is A1, A2, vector B, which is B1, B2, then the product of A and B equals A1 times B1 plus A2 times B2. Note that A1, A2 are the two components for Cartesian vector A, and B1, B2 are the two components for Cartesian vector B. So that's a dot product for vectors in the Cartesian form. Any questions? Okay, I'll give you some time to have a look at the process here. And probably you want to write the conclusion down onto your notebook. We're going to use that to solve a few example questions later. Okay, I hope you finish now. So let's have a look at the example. Calculate the dot product of two vectors u and v. Question A, given u equals 5, -3, and v is 4, 7. Question B, u is -2, 9, and v is -1, 0. Okay, I'll give you 2 minutes to have a look at this question by yourself. Okay, have we finished? So let's have a look at the solution together. According to the definition of dot product of u and v equals u1 v1 plus u2 v2, right? u1 v1 are the two components of u, v1 v2 are the two components of v. So that gives us 5 times 4 plus -3 times 7, which gives us -1. In question B, dot product of u and v again equals u1 v1 plus u2 v2, which gives us -2 times -1 plus 9 times 0, which gives us 2. Okay, any questions? Okay, if no questions, let's have a look at the main properties of the dot product. First, for non-zero vectors, u and v, vectors u and v are perpendicular if and only if the dot product of u and v equals 0. That is, if u and v are perpendicular, then we have the dot product of u and v equals 0. And if dot product of u and v is 0, then u and v are perpendicular. Also note that the zero vector can be considered perpendicular to any vector. Number 2, for any vectors u and v, dot product of u and v equals the dot product of v and u. This is called the commutative property for the dot product. And number 3, for any vector u, dot product of u with itself equals the magnitude of u squared. Fourth, for any vectors u and v, the scalar and the scalar k belongs to the real number set. K times the vector u, then dot product with vector u equals k times the dot product of u and v. So we can change the order. We can calculate the dot product first, right? Also, that equals vector u dot product with the product with a product of k with v. That means you can change the order of the k, right? K can move from the front position with u and to the second position. So we can calculate k times v first, then find dot product with u. This is called the associative property for the dot product. Okay, last, for any vectors u, v, and w, we have the following relationship. Vector u dot product with the sum of vector v and w equals the dot product of u and v plus the dot product of u and w. And because of the commutative property, this can also be written as the sum of the vectors v and w times a dot product with vector u equals the dot product of v and u plus the dot product of w and u. This is called the distributive property for the dot product. Well, actually, you can use the definition for dot product for Cartesian vectors to prove each of the properties. Okay, I'm not gonna prove all of them for you here. You can try to prove each of them by using the Cartesian vectors by yourself after this class, okay? Okay, I'll give you some time to have a look at this. And next, we're going to use some properties to solve the following example questions. All right, have you finished? Then let's consider an example problem. Can you prove one of the properties? For example, can you prove that for any vectors u, the dot product of u with itself always equals magnitude square, the magnitude of this vector squared? Okay, I'll give you 3 minutes to have a look at this problem by yourself. Okay, have you finished? Any ideas? Okay, let's have a look at the solution together. So we can let vector, well, we can let a vector A be A1, A2, right? The two components are A1, A2. So the left side is vector, the dot product of A with itself, which according to the definition, that gives us A1 square plus A2 square, right? And the right side is the magnitude of A square, which gives us the magnitude of A1, A2 square. And that also gives us A1 square plus A2 square. Therefore, the left side equals the right side. Thus, we know the dot product of any vector A with itself is always equal to the magnitude of this vector square. Of course, here we use the letter A. You can also use letter U. Okay, any questions? Okay, if no questions, let's consider another example question. Use the properties of the dot product to expand and simplify each expression. Okay, here I'm gonna I'm gonna give you 5 minutes to consider the two problems here. Okay, have we finished? Let's have a look at the solution together. In question A, this can be simplified to k times the magnitude of u squared plus k times the dot product of u and v, according to the distributive property and associative property. In question B, we know that that can be written as the sum of two vectors r and s times the vector r first, then plus the sum of vector r plus s times negative vector s. That's according to the distributive property, right? And we apply the distributive property again. That gives us r dot product with r itself plus s dot product with r plus r dot product with negative s plus s dot product with negative s. Then we can apply the associative property that gives us the magnitude of r squared plus dot product of s and r minus 1 times the dot product of r times s minus 1 times the dot product of s with s. Then according to the commutative property, that gives us the magnitude of r squared plus dot product of r with s minus the dot product of r with s minus the magnitude of r s squared. And finally, this can be simplified to magnitude of r squared minus the magnitude of s squared. Okay, any questions? Okay, if no questions, let's have a look at another concept, which is called the vector projections. Well, we can think of a vector projection like a shadow. Consider the following diagram, where the vertical arrows represent light from the above. Think of a projection of vector v on vector u as the shadow that v casts on u. First, if the angle between vector v and vector u is less than 90 degrees, as shown here, theta is less than 90 degrees, then the projection of v on vector u, or we can use this symbol to denote this kind of projection. Projection of v on u is a vector component of v in the direction of u. So here, this vector here, the purple one, is a projection of vector u on vector, is the projection of vector v on vector u. Second, if the angle between v and u is between 90 degrees and 180 degrees, as shown here, theta is between 90 and 180 degrees, then the direction of projection of vector v on u is opposite to the direction of vector u. So as shown here in this graph, again, the vector in purple here is the projection of vector v on the vector u. Okay, third, if vector v is perpendicular to vector u, then vector v casts no shadow. So if theta here is 90 degrees, the projection of vector v on vector u is a zero vector. Okay, I'll give you some time to have a look at these concepts. And after that, we'll try to solve some related problems, okay? Okay, next let's have a look at this example. Question A, find the projection of vector v on vector u if theta is between 0 and 90 degrees. Question B, find the projection of vector v on vector u if theta is between 90 degrees and 180 degrees. So you need to be careful with the projection. The projection itself is a vector, right? So you need to specify both the magnitude and direction. Okay, I'll give you 2 minutes to have a look at this question. Yeah, rigorously speaking, we should also state that theta is the angle between the two vectors, right? All right, let's have a look at the solution together. So first, let's consider question A. We can construct a segment CD perpendicular to vector AB with D on AB, right? Then we know vector AD equals the projection of vector V to vector U. From this triangle, we know the magnitude of vector AD over the magnitude of vector V equals cosine theta. Therefore, the magnitude of AD equals magnitude of vector V times cosine theta, which means the magnitude of the projection of vector V on vector U equals vector V's magnitude times cosine theta. Well, this gives the magnitude of the projection, which is also called the scalar component of vector V on vector U. The direction of the projection is the same as the direction of U. If we multiply the magnitude of a projection by a unit vector in the direction of U, we will get a complete form of the projection, right? So we can let KU be the unit vector in the direction of U. Then we can easily solve that the absolute value of K should equal 1 over the magnitude of vector U, right? Since we want the unit vector to be in the same direction as vector U, the real number K must be positive. Thus, we know K equals 1 over the magnitude of vector U. So we know a unit vector in the direction of vector u is just the reciprocal of the magnitude of vector u times vector u itself. Thus, we have the following relationship. The projection of vector v on vector u equals the magnitude of vector v times cosine theta, then times the unit vector in the direction of vector u. Okay, I'll give you some time to have a look at this relationship. Any questions, just let me know, okay? The first part of the projection in the right side of the expression is the magnitude of the projection. And the second part in the parentheses is the direction of the projection. And also in the future, if you know the angle between two vectors, you can use this shortcut to find the projection of one vector on the other vector. Okay, have you finished? Then let's have a look at question B. So the method is similar, right? From the diagram, we know the projection of vector v on vector u is the magnitude of vector v times cosine 180 degrees minus theta. And according to the trigonometric identities, this gives us the magnitude of the projection is negative the magnitude of vector v times cosine theta. The direction of the projection is opposite to the direction of vector u. Thus, we want the negative value of k from part A. So here in question B, we know the k equals -1 over the magnitude of vector u, right? So a unit vector in the opposite direction to vector u is -1 over the magnitude of u times vector u, right? This is a direction in the opposite direction to the vector u. Thus, we know the projection of vector v on vector u should equal negative the magnitude of vector v times cosine theta times the unit vector in the opposite direction to vector u, which is given by -1 over the magnitude of vector u times vector u itself. Again, the first part is the magnitude of the projection. The second part is direction, as shown here in this expression. And also we can simplify this to the magnitude of v times cosine theta times 1 over the magnitude of vector u times vector u. Well, if you compare these two formulas, the two formulas are the same, right? So in the future, you can use this shortcut to calculate the projection of vector v on vector u, given the angle between these two vectors is theta, where theta is between 0 and 180 degrees. The formula is the same. I'll give you 1 minute to have a look at the formula here. Any questions, just let me know, okay? Okay, so let's have a look at the takeaway from the previous example. Basically, this is a summary of the previous example. The projection of vector v on vector u, where theta is the angle between v and u, is given by the following formula. So we can either use this one or this one to find the projection of vector v on vector u. And specifically, if theta is between 0 to 90 degrees, the projection is the magnitude of v. The projection of vector v on vector u is given by, the magnitude of the projection of v on vector u is given by the magnitude of v times cosine theta, or the dot product between u and v over the magnitude of u. Whereas when theta is between 90 and 180 degrees, then the magnitude of projection of v on vector u is given by negative the magnitude of v times cosine theta, or negative the dot product of u with v over the magnitude of vector u. Okay, any questions? And you see why these two formulas are the same? Because the second formula can be converted to the first one. Why is that? Because the dot product of v and u can be expressed as the magnitude of v times magnitude of u times cosine theta. This is according to the definition of dot product, right? And on the other hand, we know the dot product of u with itself is given by the magnitude of u squared, right? So after simplification, we can cancel the magnitude of u. So actually, you can see that that's the same with the expression in the first formula, right? Magnitude of v times cosine theta and over the magnitude of u, then times the vector u, right? So you can use either of these two formulas to find the projection of vector v on vector u. Okay, I'll give you 1 minute to have a look at these two formulas. Probably you want to write them down, and we're gonna use them to solve some examples later, okay? Okay, if no questions, let's consider this problem, this example problem here. For each pair of vector A and B given below, determine the projection of vector A on vector B. Okay, I'll give you 4 minutes to consider this problem by yourself. Okay, have we finished? Let's have a look at the solution together. Note that we can directly use the formulas to find the projection of vector A on B, right? In question A, the projection of vector A on vector B is given by, so note here in this question, we note theta between the two vectors. So we can use the first formula. Remember, in the first formula, there is a cosine theta, right? So let's put all the values in. First, the magnitude of A is 5. Cosine theta is cosine 60 degrees. Then we also know the magnitude of B is 2. So put all the values in. That gives us 5/4 times vector B. Well, we don't know the components of vector B, so we can just leave it there. In question B, we don't know the angle between the two vectors, but we do know the components for vector A and vector B, right? So this time we can consider using the second formula. So note that in the second formula, there is no cosine theta, but instead we're going to use the dot product between the two vectors and the vector u, or in this case, vector B, right? So the projection of vector A on vector B is given by the dot product between vector A and B over the dot product of vector B with itself times vector B. Again, put all the values in. That gives us negative 52 over 25 and 39 over 25. Okay, any questions? All right, if no questions, let's have a look at the applications of the dot product. Remember, at the beginning of this course, we have learned the definition of dot product, right? So now let's have a look at some application problems of the dot product. For example, we can find the work performed using the dot product. Max is pulling his sled up a hill with a force of 120 newtons, at an angle of 20 degrees to the surface of the hill. The hill is 100 meters long. Find the work that Max performs. Round the result to the nearest joules. Okay, I'll give you 2 minutes to have a look at this problem by yourself. Okay, have you finished? Let's have a look at the solution together. Okay, there are two vectors to consider, right? The force F on the sled and the displacement S along the hill. Remember in physics, to find the work, we need the magnitude of the component of the force along the surface on the hill. Then we can label the endpoints of vector F as A and B. Draw a perpendicular from B to the surface of the hill at C. Then the length of AC is equal to the magnitude of the force along the surface of the hill. From the triangle, we know AC over AB equals cosine 20 degrees. So AC equals AB times cosine 20 degrees, which is 120 times cosine 20 degrees. From the definition of work, we know the work done is defined as the magnitude of the distance S times the magnitude of the force AC, right? Which equals 100 times 120 times cosine 20 degrees, which is approximately 11,276 joules. So the work done by Max is pulling his sled up the hill is 11,276 joules. Also note that the shortcut method to find the work done is given by the following formula. W is always equal to the force F dot product with the distance S which is given by the magnitude of f times the magnitude of s times cosine theta, where theta is the angle between these two vectors. If you use this shortcut and substitute all the values in, that also gives us 11276 joules. All right, any questions? Okay, if no questions, let's consider another example problem. Find the angle between two vectors. Can you determine the angle between the vectors in each pair? A, vector G is 5, 1, and the vector H is -3, 8. In question B, vector S is -3, 6, and the vector T equals 4, 2. Okay, I'll give you 3 minutes to have a look at this example. Which pair? Okay, have we finished? Let's have a look at the solution together. So in question A, from the definition of the dot product, we know the dot product between vector G and H is given by the magnitude of G and H times cosine theta, right? So cosine theta should equal the dot product of G and H over the magnitude of H times magnitude of H, magnitude of G, right? So we can substitute all the values in. First, the dot product between G and H is given by 5 times -3 plus 1 times 8. And then the magnitude of G is square root of 5 squared plus 1 squared. The magnitude of G is square root of -3 squared plus 8 squared. Then theta equals arc cosine -7 over square root of 26 times square root of 73. which is approximately 99.246 degrees. Then approximate to the nearest tens. Then we can conclude the angle between G and H is approximately 99.2 degrees. Any questions? Okay, if no questions, in question B, the method is actually similar, right? No, cosine theta equals the dot product of S and T over the magnitude of S times the magnitude of T. Also substitute all the values in. That gives us cosine theta equals 0. Therefore, we know theta must equal 90 degrees. So we know the angle between S and T is 90 degrees. In other words, these two vectors are orthogonal. Orthogonal, which also means perpendicular. Okay, so the main takeaway of this example is that to find the angle theta between two Cartesian vectors u and v, we can use this formula. Cosine theta equals the dot product between these two vectors over the product of the magnitudes of these two vectors. Then use arc cosine to find the angle theta. Okay, any questions? All right, if no questions, let's consider one last example. We can also use dot product in sales problem. For example, a shoe store sold 350 pairs of Excalibur shoes and 275 pairs of Camelot shoes in a year. Excalibur shoes sell for $175 and Camelot shoes sell for $250. Question A, write a Cartesian vector S to represent the numbers of pairs of shoes sold. B, write a Cartesian vector P to represent the prices of the shoes. Then find the dot products S with P. What does this dot product represent? Okay, I'll give you 3 minutes to consider this question by yourself. Okay, have you finished? Let's have a look at the solution together. Okay, question A, the vector S equals 350 to 75, right? That's numbers factor. And question B, the price vector equals 175 and 250. And the dot product of S and P equals the product of these two vectors. So just put all the numbers in. That gives us 350 times 175 plus 275 times 250, which is 130,000. So the dot product represents the revenue, right? It's the sum of the numbers times the prices of the two types of the shoes. So the dot product represents the total revenue from the sales of the two types of shoes. Okay, any questions? Okay, if you don't have any questions, let's revisit today's learning goals. So after this lesson, now you should be able to first understand the concept of dot product for both geometric vectors and Cartesian vectors in two space. Then determine the dot product for both geometric vectors and Cartesian vectors in two space. Next, understand the properties of the dot product in two space. Next, find the projection of one vector on another in two space. Last, solve application problems related to the dot product in two space. Okay, do you have any questions regarding today's lesson? If no questions, remember to complete the homework on Google Classroom and submit them before the deadline, okay? Okay, class dismissed for today. I'll see you tomorrow. Bye.